Hi there, everyone. Welcome to a special edition of ME3005. I wanted to take a time to record a video to talk about some of the calculations for the combined loading lab. I've had a lot of questions about it, and I've seen some confusion about it in some of the early lab reports. So I wanted to write a video just to clarify some things and talk about exactly what you want to do to attack these calculations for this particular lab. So I'm going to put you on the writing pad here, and we'll go ahead and we'll talk about what's going on in this particular lab with a little bit more detail. So here we are on the writing pad, and I'll just remind you that in this particular lab, we're really going to be focusing on Hooke's law. I talked about this in the end of the lab lecture for the last lecture period, so let's just remind ourselves Hooke's law. And if we're in 1D, you should have something like the stress is equal to the elastic modulus times the normal strain. And if you're in 2D, you're going to have something like the shear stress is equal to the shear modulus times the shear strain. All right. So what we're going to do in this lab, or what we hope to accomplish in the lab, is we ultimately want to calculate what is this elastic modulus E and what is the shear modulus G. So I'll put that this is like the final goal. Okay. So in each one of these two equations, we're going to need to sort of calculate what is the stress at each point of interest, and then also look at what is the strain at those points of interest. So for these equations to complete and for us to calculate the elastic modulus E and the shear modulus G, we'll need to get the values of sigma, obviously, and these are gotten from your combined loading theory. Same thing with the shear stress, combined loading theory. And then the strain is obtained from the lab measurements. Okay. Now we're going to talk about specifically what points I think are best for executing these calculations so that we can ultimately get to our final goal of calculating the modulus, both the elastic modulus and the shear modulus. So what I'm going to do is I'm going to bring in a picture of the apparatus and talk about what's happening here. So this is the picture here that's directly from your lab, and will help us define kind of the coordinate systems and pieces of interest in this particular guy. Okay, I don't know why it put it way over there. Okay, there we go. It's a little bit better. This guy up here. Okay. So here's the apparatus for our lab. You've all seen this picture before. And let's focus our efforts on what is kind of loading situation number 2, where we have this long steel rod that's coming through. And we have some load at the end of the rod here that we can just call, let's say, capital F. So we've got a couple of points of interest on the sort of cantilevered end of our bar, points A, B, and C that have strain gauges. And those points of interest are kind of shown back here on the backside. Now, we're going to look at a cross-section of interest of this particular guy, and that cross-section is going to be here. And so I'm going to just draw this particular cross-section here with a slightly different orientation. So here we should see the cross-section after kind of doing our combined loading analysis, and I'll sort of leave that to you. But like I said, we want to relocate the forces and moments to this cross-section of interest. And what you're going to find is you're going to have a coordinate system that looks something like here. We have x coming off of this face. We have y coming to the right. We have z up. So here we have x, y, and z. And after your analysis, and this is loading situation number 2, after we've put the steel rod in, you should have something like a torque that's being applied in this general direction. I'll just label it as mx. You should have a moment coming across the face here that looks like my, and you should have a transverse load that's coming across the face. I'll just call this fz. All right. Now, what we're interested in is we're interested in sort of the normal stresses giving us the elastic modulus and the shear stresses giving us the shear modulus. Okay, so we know that our points of interest on this structure where we have strain gauges are up here, and over here, where this we call point A, this we call point B, and this we call point C. Now, I'll say that with your combined loading theory, that you kind of did for homework number 1, which was sort of last week, you should be able to find let's say, the following variables. You should be able to find the normal stress on this face at point A, the normal stress on this face at point B, and the normal stress on this face at point C. Those things should be rather intuitive and rather obvious for you to handle and take care of. Okay? Should also be able to find the shear stress on the X face in the Z direction at B, the shear stress on the X face in the Z direction at C. So we'll have to remind ourselves when we look at this particular cross section, we're looking at this here is the X face, right? And we have 2 different possible directions that we could be shearing across on this particular face. The one that we really care about is the Z direction when we're talking about points B and C. So let's just dive in this a little bit more detail just to make sure it's absolutely crystal. All right. Let's, for instance, look at one of these points in detail, and maybe let's look at point B. If we were to draw a shear element at point B, our 3-dimensional element, our cube that we sort of talked about in class at point B, and we looked at what is this like stress cube at point B, you would have something that looks like this. All right. Here's your cube. And if we were to draw the stresses on this appropriately, you might go through this to determine that, okay, what is my normal stress at B? Well, the only thing that could possibly contribute is this moment in the y direction, but B lies on the neutral axis for that particular moment. So we have that sigma xx at B is going to be equal to 0. Other elements that might be of interest to us, here we have this force coming across the face in the z direction. So we have a tau xz. We're going to have a shear stress on the x face in the z direction. Also, this torque, this moment in the x direction, will also contribute some amount of shear stress at point B. Those things you'll have to calculate yourself using things like TC on J plus VQ over IT to calculate what is the shear stress at point B. But specifically, this is on the x face in the z direction. So let's draw what that shear stress might look like on this element. Here, this is shear stress on the x face in the z direction. Okay, by conservation of momentum, we sort of have to balance that out in the other direction. Here, this is shear stress on the z face in the x direction. But we know that these things are generally equivalent. All right. So when you're doing your combined loading calculations, you're going to be calculating what is this particular piece. All right, this is going to be the theoretical combined loading stress that you'll have in your piece that is going to be fed into, let's say, this Hooke's law all the way back up here. Right? So if we look down, let's say, the y-axis, that is looking down this axis. All right, I'm going to look down the y-axis at the element that I have. You should see something that looks like this. All right. Where we have our coordinate system here. That is x, z. All right, so here's your shear stress tau x, z that you're going to be using in this particular problem. All right, now when you're looking down the y-axis, what you're actually looking at here is going to be the surface of the bar, right? So this is the surface of bar at point B. And specifically, this surface has our series of strain gauges. Okay? So our strain gauges are there. Let's draw that absolutely crystal clear one more time to make sure that we're all on board with that. So if you're looking at, this particular cross section here, and you've got on this particular side, here's your point B. If we're looking at the side, we're looking at this particular view here. Okay, so here is what is x, y, z. So if we're looking at point B, here's point B if we're looking at the surface. And our coordinate system is going to be, here's x, here is z, and you're looking down y. All right. Now on the surface of this piece, we have that 3 strain gauge rosette that I sort of mentioned previously. And that is a set of 3 basically resistors or 3 strain gauges that have this general orientation. All right. In the lab, we've numbered them as here is epsilon 2, here is epsilon 3, here is epsilon 4. Similarly, on the opposite side of the bar is point C that has a gauge that also looks like this, containing epsilon 5, epsilon 6, and epsilon 7. Right? So we've calculated what the shear stress is at this particular point from your combined loading calculations. Now we need to know what is actually the shear strain at this particular point. All right, so let's make that clear. Is we calculated what is tau x z at point B from combined loading equations. And when I say we did it, you did it. Rawr. All right, now we need the shear stress in the xz coordinate system at point B to complete the following equation. Here. All right. So we calculated this from combined loading. We need this guy from our strain gauges. That's kind of the whole point of the lab. Once we do that, we can then calculate the shear modulus, G. Right? So how do we do that? Well, we need to go from the strains that we know, which is like epsilon 2, epsilon 3, and epsilon 4, to the shear stress gamma xz at B. And this is where people really are struggling. How do you take the strain measurements from gauge number 2, gauge number 3, gauge number 4, and translate that into some shear strain at point B, specifically in the xz coordinate system, so that you can marry the shear stress that you calculated in the xz coordinate system together with the shear strain to get the modulus. All right. Now, if we go back up here and we look at this particular gauge, this particular series of strain gauges, it has its own coordinate system that's not necessarily aligned with our XZ coordinate system. Okay? So if I were to look at this particular gauge, I would say its natural coordinate system is something that looks more like this. Okay? And maybe I'll call this the AB coordinate system. All right? That seems a little bit more natural for that gauge. All right, it's this 45-degree rosette where one leg is along one axis, one leg is along the other, and then you have this guy that's kind of in the middle at this sort of 45-degree angle between the two of them. Okay, so what we need to do is we need to somehow take, what is this, like epsilon 2, epsilon 3, epsilon 4, and go to something like epsilon x, epsilon z, and gamma x, z. And we're going to do this with strain transformations. Okay. So let's go ahead and take a look at this. So recall for a 45-degree rosette, the following is true. If you have some coordinate system that looks like A, B, and you have one gauge here, one gauge here, and one gauge here. Let's call this epsilon A, epsilon B, and epsilon 45, for instance. Well, we know that the following equations are true, is that, you know, the strain in the A direction is whatever the gauge A is reading. The strain in the B direction is whatever gauge B is reading. And the strain, the shear strain that you have in this AB coordinate system is going to be 2 times this epsilon 45 minus the quantity epsilon A plus epsilon B. Okay, this is what we talked about for strain gauge rosettes. So we're going to leverage this general idea using like the AB coordinate system up here to calculate what is the shear strain in the AB coordinate system. Then we can rotate that shear strain to get to the XZ coordinate system, right? So that's the general idea. All right, so in this particular situation that we have, we've got something like epsilon A is our gauge number 4. We have that epsilon B is like our gauge number 2. All right, so if we scroll up here, the strain along A is epsilon 4. The strain along B is epsilon 2. Did I write that correctly? Yes. So A is epsilon 4, B is epsilon 2. That means that the shear strain, gamma AB, is going to be a combination of 2 times epsilon 3, it's like the gauge in the middle, minus epsilon 4 plus epsilon 3. Sorry, epsilon 2. Let's be a little bit more clear with handwriting here. This is because of our strain gauge rosette equations, more or less. All right. So to finish this off, I need to transform into XZ coordinate system. All right. The way we do that is with strain transformation equations. And these were given to you in the lab lecture notes last time. And it's kind of some of the material we're talking about in lecture right now. In lecture, we're more or less doing stress transformations, but sort of the derivations for strain transformations are more or less the same. Okay, so from the lab lecture notes, we're going to end up with a strain transformation equation that looks something like gamma x z on 2. Let's actually do it this way. This is actually a little bit more accurate. It's negative epsilon A minus epsilon B on 2 times sine of 2 theta plus gamma AB on 2 cosine 2 theta. Okay, so the question then is like, what is this angle of theta? Well, the angle of theta is the angle between the coordinate system that we're working in, this AB coordinate system, and the coordinate system we want to go to, which is like this ZX coordinate system. So that angle here in this particular situation, that angle of theta, is the angle here between our AB coordinate system and our ZX coordinate system, which here is going to be sort of this angle, which is theta equals 135 degrees. Okay, so here in this situation, from A, B to the X, theta is 135 degrees. All right. So in closing, if theta is 135 degrees, this guy is going to go to -1. Theta is 135 degrees, this guy's going to go to 0. All right. The sine of 270 is -1. The cosine of 270 is 0. So what that means is, in closing, you'll have like gamma ZX, which is going to be simply epsilon A minus epsilon B, or in terms of the strain readings from the lab, specifically at point B here, is going to be epsilon 4 minus epsilon 2. Okay. So, can also use strain transformations to go from, let's say, epsilon A, epsilon B, to the normal strains epsilon X and epsilon Z, specifically at point B. Similar looking equations, but slightly tweaked because we have different transformations. And if you do that, you'll have something like epsilon X, specifically at point B, is going to be epsilon 3. I think that's pretty intuitive to see. Sorry, this 3 is a little jacked up. I think that's pretty intuitive to see, that the strain in the X direction is just going to be the strain that you measure with gauge number 3. And that's because here, this gauge number 3 is strictly in the X direction. So it's pretty easy to see that we should be measuring the strain in X with gauge number 3. Also, if you do this well, you should find that the strain in the Z direction, which is sort of this normal strain at point B, is epsilon 4 plus epsilon 2 minus epsilon 3 here. Okay. So we've calculated what is the strain in the X direction at B, the strain in the Z direction at B, and also the shear strain at B in the X and the Z directions. And we've done it in terms of the readings of the gauges from our labs, gauge 2, 3, and 4. All right. So we can actually present this in sort of a matrix format if we'd like, all together. Which looks something like the strain in X at B, the strain in Z at B, and what is the shear strain XZ at B, sort of this vector quantity, is equal to the matrix that looks like this. So this here, this transformation matrix, is given to you in the lab. I think people were a little bit confused about where this came from and what it represents. But hopefully, through this lecture, you sort of understand that there's strain transformations required, some knowledge about how the strain rosette gauges work to ultimately get to you the information about the strains at these particular point of interest. Okay, so after executing this, you should have like strain xz at b, and you should also have tau xz at b from combined loading equations. So you should be able to do this. And calculate your value of g. See if that value of g matches up with normal values of g for aluminum members, and make a report and tell me all about it. Okay, so that'll conclude everything I have for now. Appreciate you kind of watching this and sticking this out if you're having problems with the calculation. I hope this helped. And I guess I'll see you next time. Bye-bye!